Hello, welcome. This is AQA's A2 Unit 5, the normal Section A nuclear and thermal that everyone does. Okay, so this is the obviously June 2016 paper. I want to start off by saying this was the paper I did last year. Excuse me, and I found it at the time quite a difficult paper. Sorry, because of my throat, but I think overall, looking back at it, it's probably not so difficult. Okay, so what I'm going to do when I go through this paper is point out areas where I struggled on last year. Okay, so if it helps you to think of this in the exam. Now, obviously, if you're doing this paper this year, it's quite clearly a resit, as per myself. So it is kind of crucial in a way that some of this won't be asked. Okay, so the 6 marker won't be the same as last year, so you can kind of take gratitude from that, but as I say, that's totally and utterly up to you. Okay, right, so kicking off with question 1, it's talking about electron diffraction. So all this question is about electron diffraction. Kind of brings up the idea, probably not going to be asked next year, this year even, but who knows. Okay, so it says that a electron diffraction experiment, a beam of them, electrons, is fired at oxygen-16 nuclei. Each electron has an energy of 5.94 times 10 to the minus 11 joules. The approximation, momentum equals energy over the speed of light, can be used for electrons at this energy. Okay, and we're asked to calculate the wavelength of the Broglie wavelength of electrons at this level. Okay, so the first thing we need to do is note down what we've been told, okay, whether it be relevant to this particular question or not, okay. So it's 1A and this is part 1. So we're told that the electrons have an energy at this speed of 5.94 times 10 to the minus 11 joules. Okay, that's their energy. And we're just told, straight after that, that in this particular case, we can say that momentum, denoted by little p, is equal to the energy, E, over the speed of light, C. Okay? So, quite clearly, you wouldn't have told us this if it wasn't relevant. Okay? So therefore, we're going to need to do something with momentum. But that's not answering the question. It's not asking, calculate the momentum of the electrons at this energy. It's saying, calculate the de Broglie wavelength. So we're going to have to go a bit further. So the first thing I would do is note down the de Broglie wavelength, which is h Planck's constant over mv, or in other words, Planck's constant over momentum, p. Okay, and we know what h is. Obviously, it's given in the formula sheet. You should know that anyway. But this momentum is what we're meant to find out. Okay, and we're told that momentum is equal to the energy over the speed of light. We know the energy, we know the speed of light. So therefore, it's just a case of first off working out the momentum and then put it into the Broglie wavelength equation. And we're actually told that it should be, when it's a show that question, you don't get a mark for the answer because it tells you the answer. Okay, so anyway, it should be about 3.3 times 10 to the minus 15 metres, if we get it right. Okay, so let's first work out the momentum, which is 5.94 times 10 to the minus 11 joules over 3 times 10 to the 8 metres per second. Okay, now you don't need to put the units for this, obviously, but it's up to you. Okay, so that will get you your momentum. It should be equal back to 1.98 kilogram metres per second. Sorry, 1.98 times 10 to the minus 19 kilogram metres per second. I got kilogram metres per second because that's the SI unit for momentum. But obviously you could also work it out as joules per metre second. Okay, but as I say, it's up to you. It's just easier using that because you know the units are not right. But it doesn't really matter because we're not going to be using them units overall. Okay, so now we know momentum, and obviously Planck's constant is 6.63 times 10 to the minus 34. You don't need any calculation to work that out or look in the formula sheet. over momentum, which we now know is 1.98 times 10 to the minus 19 kilogram meter per second. Okay, now I would use the answer, I would have that saved 1.98 in your calculator, okay, and then just copy it across into the formula where it's 6.63 times 10 to the minus 34 over the answer that you saved in your calculator, which gives a more accurate reading. Okay, so therefore you should get about 3.3 times 10 to the minus 15 metres. Or I got 3.35, but it's about that, okay? Times 10 to the minus 15 metres. And I prefer them show that questions because you know if you get it right or wrong, even though you don't get a mark for the answer, but it doesn't really matter, it's 1 mark, isn't it? So anyway, if you didn't get that, then just have a quick reference over what you could have done this. Okay, I think I probably got that right in my last paper. Now this next bit kind of uses a diagram. So because the paper is now online, obviously you can look at the paper online yourself and look at this graph. But I'm going to do a quick sketch of it. So basically what we've got is it's showing the intensity of the diffraction beam, okay, from this electron. Okay, so it looks something like that. Whereas on the y-axis we've got the intensity, and on the x-axis we've got the angle or degree. Okay, so how's this going to help us answer it? Obviously I've just joined up the dots here, but you could say you can look online for that video. So, what are we told? So, we're told that the angle of the first minimum in the diffraction, electron diffraction, is given by sine theta over 0.61 times the wavelength over the nuclear radius. So we are going to be using this answer here. Now, the key thing of this, basically, right, okay, so I'll write it down. So sine of the angle, okay, is equal to 0.61 times the wavelength of the electrons over the radius. One thing I just want to point out before I answer this question, the first diffraction, electrons will only be diffracted if the wavelength is the same size as the radius of the nuclei, okay? So that's how this equation is derived, the theory of that, but as I say, that's given to you, so we're only going to have to use that. The key wording in this first part of the question, which I probably don't think I read in the exam, the first minimum, okay? So basically, the first minimum, there's no point looking at the radius because we're going to calculate that out, okay? The only thing we can tell from the graph of the first minimum is the angle. So the only thing we've got in there to calculate is the angle to find from the graph. Okay, so we need to look where the sine theta, the theta angle or degree, lines up with the first minimum. Okay, so we'll look at the graph, and obviously quite clearly the first minimum is this point here. So you draw a line down, and you should get about 42 degrees. Okay, so we're going off in degrees because it's not maths, not in radians. Okay, so I would keep it as degrees because that's what it says here as well. So the theta is equal to 42. So sine of 42 equals 0.61. Now you get an error carried forward mark if you didn't. Actually, I don't think you would. If you didn't get, basically, if your answer for A part 1, okay, was incorrect, but you're told that it's a show that question, okay, so it gives you the answer, in other words, of 3.3 times 10 to the minus 15 metres. So regardless if you got the wrong answer in part 1, you don't use that answer because you know it's wrong. You're showing the examiner you know it's wrong. So you don't get an error carried forward mark for that. Okay, so in other words, what you have to do is use the wavelength of 3.3 times 10 to the minus 15 metres if you got it wrong. Okay? So basically you put in your answer the 3.3 times 10 to the minus 15 metres over the radius, which you don't know. Rearrange to get the radius as a subject, so therefore the nuclear radius is what you want to work out. It's 0.61 times the wavelength, okay, over the sine of 42, where your wavelength is 3.3 times 10 to the minus 15 metres. Okay, shove that all into your calculator and you should get an answer of about 3.1 times 10 to the minus 15 metres. Okay, now a key thing to work out here is that this will have to because of what I said before about the fact that the electrons will only be diffracted if the wavelength of the electrons is the same as or greater than the radius of which it's being compared against. Okay, so in other words, if your answer part 2 was higher than 3.3 times 10 to the minus 15 metres, you know you've got it wrong. Okay, so look at the guidance there, but it doesn't really matter if you don't get that. I'll explain it in another video. If you just comment on this one, I'll create another video explaining that. But I think that's already in the pipeline anyway to come up on the channel. Okay, so anyway, that's the radius. So let's look at the next part of the question. So this next part is basically asking you to be part 1. So we're on to 1B now. 1B part 1. It's asking you to show or kind of draw the diagram of Rutherford's equipment. Okay, in his scattering, alpha scattering, where he's trying to work out the size of the nucleus. Okay, what it's made up of. So obviously, the first thing you need to do is have your alpha source, and your alpha source needs to come out and kind of hit this piece of gold foil. And obviously you need to show some being diffracted, electrons, and some going straight through, and then you need a detector on the other side. Okay, now there's a few things wrong with that, okay, but I didn't go into too much detail because I want to just go through the bits that you need to add on. So that's the basic of what you need here. So we've got an alpha source, we've got the gold foil, and then we've got a detector. They're the 3 key things you need to help you answer this. However, we need a bit more detail than just that, okay? Because with the angle of this, we need to show that the alpha source is coming from different angles. Okay, so you're going to draw more than one alpha source, okay? And because the detector at one single point is not going to detect absolutely everything, it's just going to detect the electrons at that one point, you need to show the detector in more than one space too, okay? Obviously you can look on the mark scheme for the criteria as well, but I'm just explaining it to you now. The third thing that it says on the mark scheme that you need to be aware of is the fact that this gold foil is not 2D, okay, it's not a flat plane, it is kind of curved as well, okay, so in the mark scheme it says you can either show this by either having the alpha at different angles and the detector at different angles as well, or you can simply draw the gold foil as a 3D object, which obviously it is. Sorry. So you need to show the gold foil as something like that, okay? If you didn't want to draw the detector more than once. Okay, so hopefully that explains it to you. But as I say, it's only worth 2 marks, so it's not the end of the world. Now, I'm just going to give you a second to copy this down because the next part of 1B is the big 6 marker for this paper. Okay, and essentially this is asking about Rutherford's scattering experiment. Okay, so using that logic, it's not likely going to be asked in this paper, in the next year's paper, 2017. But anyway, it's worth going over. As I say, it's part of this paper and you might not be doing this exam. Okay, so hopefully, I think I've given you enough time there to copy that now. But as I say, all of that is on the marks, obviously online as well, so you can just have a nose if you missed anything there, or obviously rewrite. Okay, so with these 6 mark questions, I always advise writing it in bullet points, okay, rather than as a whole paragraph, because A, it saves time, B, it stops you repeating yourself, and C, well, it's just quicker, even though I've already said that. Right, okay, so as I say, this is asking you to explain Rutherford's scattering experiment. Now with all 6 mark questions, in the description of the question, it lists bullet points of what you're expected to say. And it's, in essence, there are three things to this. It's asking you to explain what was seen and what this means, okay? So in other words, for example, I'm going to list all these down anyway, but I'll just go through it to show you what I mean. Asking you to show what's seen. So say only some of the alpha particles were deflected, okay? So that obviously means most went through. So therefore this observation, okay, so they're observations, that's all it is, an observation that some of them were deflected and most went through. Okay, so therefore what does that actually tell you about the nucleus of the atom? Okay, well it tells you that there's a lot of empty space, but there is a concentrated positive charge, okay, which we obviously now know as protons and neutrons, but they didn't back then. Remember, this was the idea. This idea was being tested at the same time that the current theory of the atom was the plum pudding model of the atom. Okay, where it was thought that it was all kind of, there was no empty space. Okay, but that's a different video altogether. So if you're not sure about the plum pudding of the model of the atom, do research it, because you might be asked on it in well, you will be asked on it at some point in A-level physics. Okay, so anyway, that's an example of what it's asking. But as I say, I list a lot down. And then the third point it's asking you to explain, okay, is how these observations, that what was seen, place an upper limit on the size of the nuclear radius, which is kind of almost kind of a trick point, because you're likely to explain it anyway when you're talking about the observations and what was seen, but it's just asking you to go into a bit more detail about the what it means as a size of the nucleus. Okay, so all that third point really wants you to say is that there's a very small concentrated centre to the nucleus. Okay, right, so let's go through this as a proper exam. Now you can look on the mark scheme for exactly what it wants you to say, okay? So let me just get to it. With all these 6 mark questions, it's always, whenever you look on the mark scheme, it's always kind of, a lot of it is waffle, okay, for when it's explaining the 6 mark questions, because obviously people write it in such different ways. But in all these mark schemes and 6 mark questions, it always says, this is what you need for 6 marks, this is what you need for 5 marks, so I'll just go through that. For 6 marks, you need all but 3 bullet points covered in full, which is, you know, the bullet points that in the description of the question that I mentioned. And obviously you get marks for spelling and punctuation as well in this. So maybe set aside a mark or 2 for that. But anyway, I'm sure if you're marking it yourself, you probably spelled it right. Right, okay, so there's quite a few different points in the mark scheme, okay. So and it is quite difficult to go through really, but I'll try my best to kind of explain. Now you don't need to cover every single different bullet point in the mark scheme, okay, that it lists if you're looking at the mark scheme now. But it's really just, if you just think about it, it's not that difficult. Okay, so as I say, what it's asking for is the main observation, what this means, and how this shows an upper limit on the nucleus. Okay, so obviously the main observations that were seen, okay, were the fact that some were, what I mean by obviously some is alpha particles were deflected by more than 90 degrees. And if you want it to be really showcase your ability, you could say some, and in brackets you could put 1 in 1,000. Okay, alpha particles were deflected by more than 90 degrees, but you can just put some were deflected by more than 90 degrees if you want, get the same mark. So most particles, so obviously that says that, so most went straight through. Okay. And they're the main observations. Really. So that's really the main observation. You need to talk about the fact that most went straight through, which was obviously the most surprising thing because they didn't expect that. So then you need to say what this actually means. Okay? So if all of them kind of really went straight through, this shows that the atom, that the nucleus even, is mostly empty space. Okay, so it's a key point you need to make. Okay, so that's one result of the observation. However, you need to also reference the fact that why were some deflected by so much? That they mostly empty space, and not all of it's empty space. So therefore you need to say what was causing this deflection. And then you need to say, but the fact that some were deflected by more than 90 degrees shows a concentrated positive charge. A concentrated positive charge. Okay. So we've kind of really explained the two key points there. So we've got four other. If you look in the mark scheme towards the bottom of the question, it says quick checklist. Okay. So we've covered 4 of the 6 points there, there's 2 more to go. So, what we need to now say is why this puts an upper limit on the nucleus. Okay, so to get the final 2 marks of this question, we need to talk about the fact that to find the radius, we need to concentrate on the amount that has been scattered by more than 90 degrees. Okay, because if it's scattered close to 180, it's not actually touched the surface of the nucleus. Okay, so your next point needs to be some reference to the fact that how we're going to find the radius. Okay, from this. So what you would do is look at the amount that has not touched the nucleus itself, i.e. gone straight through, and the amount that has been deflected back. So your next point needs to be some reference into looking, observing the amount of deflected alpha particles to the amount that weren't deflected. And obviously comparing these will allow you to see the actual size of the nucleus. So that will allow you to work out R. In other words, the size of the nucleus radius. So that's really all you need to talk about. Okay? So therefore, it can only be so big because most of them pass through. Okay, so that's really 3 or 4 key points you need to make. Okay, so that's the end of question 1. It's worth 11 marks. Hopefully you got most of that. I don't think I would have got this third part here. Talking about the upper limit of the radius, probably would have just got focused on the explaining them two in the exam. I think that's probably what I did. And the graph might have been a bit confusing as well, but do read the question properly because it says first minimum. So you look on that graph in B part 1, okay, where it hit the lowest point first. Okay, so any questions about this paper, please do leave a message. I will send over, there are probably model answers already out there, but if you do have any questions, please let me know. I will be creating a mock paper very soon, so if you've run out of AQA papers to do, please do send me a message on the video. Drop in your email address if you'd like to put it on, or you can message me directly. I do have a Facebook page as well if you want to message that instead. So it's obviously just the title of the channel, Bill7187 YouTube. It's on Facebook, so you could drop us a message, and I will send you over some papers and some revision guides that I've been creating for Unit 4 and 5. So thanks for watching, and we'll see you in the next video.